In 4.3, we are going to learn about metallic bonds. This will be the last part of Unit 4, intramolecular bonds. So we are going to look at two major topics in the overview of this subject: the structure and properties of metallic bonds, especially the Electron Sea model, explaining how atoms and electrons are spread out in a metal. And then we are going to look at the structure and functions of metals and alloys. Alloys are mixtures of metal. Pure metals can be anything in blue over here, and alloys can be made with metals, metalloids in green, and some of the non-metals. So let's first look at the structure of metallic bonds. You can draw this diagram for a metallic bond. It is also called the Electron Sea model. So inside a metal element, you have bunches of atoms, but not like in a normal solid where you have atoms hanging out together. These atoms have lost their valence electrons and they form cations, like I have shown over here, and their valence electrons freely move around the metal ions so that any other metal can be attracted to them. We call these detached electrons, valence electrons, also known as delocalized valence electrons, as they are far away from the parent cation. Metallic bond is a electrostatic attraction between the metal ion and any of the metal valence electrons in the sea of delocalized valence electrons around the metal ions. We call this the Electron Sea model. Delocalized metal valence electrons are responsible for many metal properties. We will discuss them further: electrical and heat conductivity, ductility, malleability, as well as the shine of metals. So, which one, sodium or magnesium, has a higher melting and boiling point, and why? If I ask you a question like this, how would you answer it? So if you draw their Electron Sea models, you will have, say, for each metal ion in sodium, which is a group 1a element, it has only one valence electron, so you will have a +1 charge and one valence electron. For the group 2a magnesium, which is in the same period, same shell as sodium, will have a +2 charge and it will lose 2 electrons for each atom. So that means you have a lot more valence electrons circling around the two plus charges than you have electrons circling around here. And also, since you have only a +1 charge here, you can only pull electrons with that amount of strength coming out from the nucleus of these ions. Here you have a +2 charge, which is much stronger than the +1, and you have much more electrons. So group 2a elements will make stronger ionic bonds because the charge from the nucleus is stronger and they have much more electrons. So you could guesstimate that the pull from the nucleus to the electrons and their bonds would be twice as stronger maybe than sodium, and this would result in having higher melting and boiling temperatures. So let's look at properties of metals. All metals are dense and they are tightly packed atoms, or ions in this case. They form compact solids at room temperature. Exception is mercury, which is a liquid at room temperature. Here are some examples of copper, showing this goldy orange color, and lead dark silver color, tin, zinc, aluminum used in aluminum foil, and the tester Cybertruck is made out of thick sheets of aluminum alloy, and nickel. Now stainless steel is made out of iron and carbon. It's not shown over here. These are good electrical conductors as they have a readily mobile valence electrons in the electron sea, and these can be transferred in the electric current. They conduct heat very easily because the electron sea heats up very fast by absorbing thermal energy. The shared electrons mobility is why metals are malleable. You can hammer them into shape, or ductile, which means stretched into wires. The color, the shiny color of metallic elements, they're all shiny, maybe except for this guy. It's because the electron sea easily absorbs light and emits light energy. They also have high melting and boiling points in general compared to other compounds. This is, the stronger the melting and boiling point, the stronger the bonds. Like in our example, magnesium versus sodium, magnesium has stronger metallic bonds. And they form ionic bonds with nonmetals. And they donate electrons in chemical reactions and form cations. Their reactivity increases going down a period and going from left to right a period. I'm sorry, I forgot to write that down. Now let's look at our third topic, metal alloys. If I ask you what a metal alloy is, your answer would be it's a mixture containing one or more metals or a mixture of metals and nonmetals. There are two types of alloys, substitutional alloys or interstitial alloys. Substitutional alloys, as the picture shows here, you substitute some of the metal positions to another metal or a non-metal of a similar size. But there are spaces between the large atoms that are even. And you could make a substitutional alloy with not just one substitution but two different or three different elements. Interstitial, inter means between, the interstitial means between spaces. This one you substitute not a substitute, you insert a smaller metal or non-metal atom between the spaces left behind by the other metal. Mind you, you can make a metal alloy which is a hybrid of both of these. You can make a substitutional alloy and substitutional and interstitial alloy. That would be even stronger. So now, important thing to remember is these guys are much stronger than these guys. And if you make a interstitial alloy that is also a substitution alloy with the strongest metals with the strongest metallic bonds, then your alloy will be really tough. So here are some uses of metals for making cookware, like cast iron pans, steel bridges, frames of buildings, making vehicles, and the Tesla Cybertruck has these weird angular angles because it's made out of straightforward sheet of thick aluminum alloy, which you can't bend to curvy structures. And so they can only fold it with a small fold like this, and that's why you have this structure. And here's some gold jewelry. And examples of alloys would be bronze, which is made out of copper tin plus either aluminum, manganese or zinc. And cast iron, which is a mixture of iron, carbon and silicon. And then steel, which is also a mixture of iron and carbon but lacking silicon. So this steel is an interstitial alloy, whereas cast iron is a interstitial alloy with some substitutions with silicon here and there. 12 karat gold is gold plus a little bit of silver. So why is steel stronger than cast iron? And explain your answer. So you would say that they are both made out of iron and carbon, but in steel you don't have silicon. Silicon is not a metal. So the valence electrons of silicon will not be sent into the neighborhood, and there wouldn't be strong metallic bonds where steel is, where the iron atoms are hanging out with silicon, because silicon is a metalloid. It doesn't really behave like a metal. Whereas steel is only made of iron, which has strong metallic bonds, and the spaces between the iron atoms are iron ions, not atoms, are filled out by the tiny carbon atoms, making it really strong. So that's why you use steel to make strong things, not cast iron. So here's a question for you. Match the description with the correct metal alloy. So I've given you 3 pictures. So this one is the metal element. So which one? Pause and figure out which ones are which. Okay, so these 2 are substitution alloys, and this one is an interstitial alloy. And which one is stronger? It's the interstitial alloy. And finally, a summary. Metallic bonds are formed when metal ions are attached to valence electrons of other atoms in the electron sea surrounding metal ions in the structure of a metal. The strength of a metal increases when the charge of the metal ion and the number of valence electrons around it increase. So the more the charge of the metal cation and the more valence electrons swimming around it, the stronger the metallic bond. Number 3, alloys are mixtures of metals made with other metals or non-metals to change the properties of the original substance. Substitutional alloys have other metals or metalloids substituting the position of the metal. Interstitial alloys have a smaller non-metal or metal occupying the smaller spaces around the major metal ions. Heat and electrical conductivity, malleability, and ductility, as well as the shininess, are all metal properties attributed to the sea of valence electrons around metal ions in the metal structure. That's it from me. Do the exit ticket now.